generic equation that includes any kind of algebraic equations and ODE, ordinary differential equations, up to second order, both homogeneous and non-homogeneous. This is basically very, very generic equation, right? The only thing that I'm saying here is that the equation that I'm trying to solve has this parameter epsilon, which is a small one. So this is the information that I would like to employ in order to simplify eventually the equations, in order to find some approximated solution to the equation. So the typical method, well, the simplest method, which is also the method that usually is not going to work for most of the problems that you are facing, that you are going to face, is what's called the regular perturbation method. So what's the idea? The idea is that you assume that the equation has a the idea is that the equation admits a solution y of t that can be expressed in the form of a series where higher order terms in the series are subleading. More specifically, what I want to assume is that my solution y of t can be written as a y0 of t plus a term which is of order epsilon, so epsilon y1 of t plus terms which are higher and higher order in epsilon. So I have terms which is epsilon squared y2 of t plus blah 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 blah. You will have epsilon to the power n yn of t plus etc. Okay. Usually what we want to do is to try to solve these equations up to a certain order, because basically means that you are approximating your solution up to the order, I don't know, for example, if you stop here, you are approximating the solution up to the second order in epsilon. Since epsilon is very small, this means that epsilon squared is going to be very, very small. So it's going to be some kind of terms that could be interesting for some phenomenon, but usually you can also stop to the first one. So the idea, what is the idea then? The idea is take this thing here, substitute this y into the equation, into your problem. Here for the moment I'm forgetting about auxiliary conditions, right? I should have some initial value problems, or possibly I should have some initial conditions here. For the moment, let me forget about that. I mean, we're going to speak about this in a couple of minutes when we are seeing the application of the methods to ODEs. So the idea is that I take this y of t, I put the y of t in the equation, and then what I do, what I will have is some kind of equations in which I have the different, I can factorize the epsilon, so I will have some tower of factors of epsilon, and just to equate right hand side and left hand side, and I will have some equations for y0, y1, y2, and so forth and so on. It's better and better to show you an example rather than describing this thing, which is a mess. So let me start, for example, with the very simple algebraic equation. The algebraic equation is x squared plus 2 epsilon x minus 3 equal to 0. Note, I'm not assuming a differential equation. This is not a differential equation. This is just algebraic. Indeed, you are very, very good in this. You can solve this directly by solving the second order equation, right? So, what is the regular perturbation method tell me? telling me. So I can look for a solution x, which can be written as x naught plus epsilon x1 plus epsilon squared x2 plus higher order terms. We'll forget about again higher order terms because up to second order is more than enough. So what I should do is to take this ansatz means a guess of the solution, and putting the guess here inside the equation. So the first term is x squared. So this is x naught plus epsilon x1 plus epsilon squared x2 plus higher order terms squared. Then I have plus 2 epsilon times x, which is again x naught plus epsilon x1 plus epsilon squared x2 plus higher order terms minus 3 equal to 0. All right, very good. Now, what's the square root of this guy here? Well, it's the x naught squared. Then I have plus the square root of this term, which is epsilon squared x1 squared, plus the square root of this other term, which should be epsilon to the fourth. I don't care about epsilon to the fourth terms. I just want to stop to the epsilon squared terms. So let me forget about this. What other terms do I have? Well, I have terms which are coming from this times this, which is going to be like 2 x naught epsilon x1, right? And then I have a term which is going like this times this other one, which is going to be 2 times x naught times epsilon squared times x2. And then any other term that I can build out of these terms here in parentheses is going to be of higher order. It's going to be something like at least epsilon cube. So I don't care about this. Just let me leave this the terms up to the second order. Of course, this again depends on the problem. If I would ask you, should look for the correction up to the third order, you should also add here all the terms which are going like epsilon to the cube. Now I can look at the second part. So the second part is going to be some twice epsilon times x naught. Then I have plus twice epsilon squared x1 higher order, because already if I'm multiplying 2 epsilon times epsilon squared x2, I'm already arriving to 2 epsilon cube x2, so I don't care about this. Minus 3 equal to 0. Right. Now what I have to do is to collect terms which have the same power of epsilon. So the first power of epsilon is epsilon to the power 0. The terms with epsilon to the power 0 are this one, x naught squared, and this one, minus 3. X naught squared minus 3. Then I have the terms which are of order epsilon to the power 1. What are the terms of epsilon to the power 1? We have this one, which is 2x naught x1, and then I have this one, which is plus 2x naught. Nothing else. No. Then let's check for the terms which are of the second order in epsilon. And these terms in the second order in epsilon are this, which is x1 squared plus this, which is 2x0 x2 plus this other one, which is q plus 2x1 plus multiples. So here other terms, don't care, equal to 0. Correct? That's correct. Now, what's the idea? The idea is that you have to equate the two sides of the equation, correct? So the idea is that terms which are carrying some certain power of epsilon are independent from terms which are carrying instead another power of epsilon. So what you have to do is to equate to 0 the single terms, the single factors of powers of epsilon of increasing order. In order to find this approximate solution, what you have to do is you equate x0 squared minus 3 equal to 0. Then you have 2x0 x1 plus 2x0 equal to 0. And then x1 squared plus 2x0 x2 plus 2x1 equal to 0. And so forth and so on. All right. Now, the solution for the first equation is something like it is x naught equal to plus minus the square root of 3. The solution of the second equation, well, here you can simplify the x naught, is going to be x1 equal to minus 1. What about the third equation? Well, x1 squared is equal to 1. And then I have plus 2 that multiplies x2 times x naught, which is plus minus square root of 3. And then I have plus 2x1, which is minus 2. This should be equal to 0. Now, 1 minus 2 is minus 1, plus or minus 2 square root of 3 x2 equal to 0. Right. Which gives me the possible solution for x2, which are minus plus 1 over 2 square root of 3. Yeah. That is. All right. Sorry, this is plus minus, it's not minus plus. Correct? Yes, it's plus minus. So now what we have to do is, well, just to collect all the terms. So what we will have is that x, the entire solution of the equation, the approximated solution of the equation. You remember we actually wrote it in this way, so it's x naught plus epsilon x1 plus epsilon squared x2 plus other terms. So x naught is plus minus square root of 3. x1 is minus 1, so this is minus epsilon. And x2 is plus minus 1 over 2 times square root of 3. So this is plus minus epsilon squared 1 over 2 square root of 3 plus higher order terms. This is the approximated solution. So these are two actually approximated solutions. The first approximated solution is for the sign plus, so it's x1 if I choose plus here and here. So that's actually why you should pay attention. It was not minus plus here because otherwise I would have had some wrong approximate solution. Okay. So the first solution is when I'm choosing the signs which are up. So it's square root of 3 minus epsilon plus epsilon squared divided by 2 square root of 3 plus higher order terms. And the second solution, approximate solution, is minus square root of 3 minus epsilon squared over 2 square root of 3 plus again other higher order terms. What you can do is to compare the approximated solution that you find with the regular perturbation method with the exact solution. In this case, this is a simple algebraic equation. You should be able to compare the two things. Indeed, you can write the solution, the exact solution of the equation. What was the equation? The equation was x squared plus 2 epsilon x minus 3 equal to 0. So the solution is some x equal to 1/2 of minus 2 epsilon plus or minus 4 epsilon squared plus 12, which is 1/2 of minus 2 epsilon plus minus 2 that multiplies the square root of epsilon squared plus 3, correct? 3 by 4 is 12, that's correct. So I can simplify this 1/2 with these guys here. What I get is minus epsilon plus or minus the square root of epsilon squared plus 3, which I can write as minus epsilon plus or minus, what I want to do is to pull out a square root of 3. So what I can do is to put here the 3 and write this as epsilon squared divided by 3 plus 1. In such a way that I can also put outside this square root of 3, no? I can write as minus epsilon plus minus square root of 3 times the square root of 1 plus epsilon squared divided by 3. Why I'm doing this? I'm doing this because now I know that epsilon is a small number, is a small parameter, so epsilon squared is a small parameter. Epsilon squared divided by 3 is a small parameter. So I can approximate this square root with 1 plus 1/2 of epsilon squared divided by 3. Correct? Is this a scandal? A little bit. So if I have something like like this, 1 plus some x to the power 1/2. When x is small. Do you know that this is true? This is basically what you obtain if you are Taylor expanding the this quantity around small x. Okay, and this is actually exactly the same. So I'm assuming that the small parameter, my x, is epsilon squared divided by 3. This was something like that. This is some approximate solution, right? I'm taking the Taylor expansion of the square root, so that's not some exact thing. Here I should have written higher order terms in epsilon. So what is this? This thing here is, let me readjust the terms. Here I have the first term, which is linear, which is the term in the power 0 of epsilon is this one, which is plus minus square root of 3. Then I have the term which is linear in epsilon, which is this, minus epsilon. And then I have the term which is in epsilon squared, which is plus or minus epsilon squared times, no. Was what that was a plus or minus terms that disappeared. Come on. Plus or minus what, epsilon squared times square root of 3 divided by 2 times 3. So I can rewrite this as this ratio here as 1 over 2 square root of 3. Great. That's finally the result that I was looking for. Again. Okay. So, what did we have just shown? We have solved the problem using regular perturbation method. So, assuming that the solution of the equation can be written in this way here, and solving the equation for these ansatz. And what we found are this approximated solution. Plus minus square root of 3 minus epsilon plus minus epsilon squared 1 over 2 square root of 3. Then we have solved the problem in the exact way. So we have just solved the second order algebraic equation. We found the roots of this second order algebraic equation. And what we found is that the approximated roots, so the roots that I obtain for small, well, the exact roots are these ones, but the approximated ones, so the roots that I obtain for small epsilon, are exactly the same that I obtain by the regular perturbation method. So in this case, for the these algebraic equations, the regular perturbation method works. So expanding, looking for an answer, looking for a solution which has some specific form of the answers, allows me to find then this approximated solution. Now let's try what happens instead with the node E. we are here for trying to solve differential equations. So let's try to see if it's possible to apply the same method to ordinary differential equations. So I will apply then the method to this equation. That's a equation of a body of mass m, which is moving in some resistive medium. So in a medium which is presenting some resistivity to the movement of the body. So what's the equation describing, ruling the phenomenon? That's well, what I have to do is to write the second law of dynamics. So ma equal to f, m the squared, what's the notation? X, the squared x in the tau squared equal to the force. So what's the force that is acting on this body? I'm interested in looking at this kind of forces, minus a the x in the tau plus b the x in the tau squared. So basically I have this point of mass m which is moving in some medium, like for example can be just moving in the air, in water, wherever it is. And this body is experiencing some resistive force that depends on linearly on velocity, with the further correction that depends quadratically from velocity. Okay? And I want to solve this with some initial conditions. What I'm saying is that the velocity at time t, at time tau equal to 0 is equal to some velocity v naught. So what's the idea of what is the approximation here? Actually here, if A and B are completely unconstrained, you cannot approximate at all. But what you can do is to approximate the equations if you have that 1.2, for example, B is much smaller than A, which is something that you would expect, right? So because you can expect that most of the resistivity is coming from the fact that you are moving, that your body is moving with some velocity v, then this would be some kind just of correction on top of the usual resistivity term due to the velocity of the body in the medium. Fantastic. So this is the problem that I want to solve, that I can rewrite in a more concise way in this way. Here I have mass times the derivative of the velocity with respect to tau minus a times the velocity plus v times the velocity squared, with velocity evaluated in tau equal to 0 equal to capital V naught. And of course with the constraint
Again.
Yeah. Just a second, because there is somebody which is trying to enter and cannot, trying to admit in the class. And if it was able or not. But in any case, let's continue. I cannot stay here every 3 seconds to try to admit this guy in the class. Yeah.
Why the second term with the B as the plus? It's not the resistance.
In principle, actually, this is just, I'm not interested in the sign of the extra term correcting the resistivity. Basically, what you can do is to try to study what happened even if you are changing the sign. Usually, what you do is the kind of corrections that you have are always working in the opposite direction with respect to the main term. So the resistivity term is going as the velocity, and usually the correction is going it's correcting in the other direction. So the resistivity term is with the minus, and the correction to resistivity is going on with the plus, and the correction of the correction is going with the minus, and so forth and so on. At the end of the day, then A, B are just constant. So these are something that then you should find phenomenological. If you do an experiment and you discover that B is negative, well, that's okay, that's fine. Just put the B that is negative. The discussion of the solution of the equation will not change if you are changing eventually the sign of B. Would change if B becomes of the order of magnitude of A, because then I cannot consider anymore this as a small correction on top of my equation. So why? Because what's the idea now? The idea is that I'm solving the equation in an approximated way. So using the regular perturbation method, I would like to find an approximated solution of my problem. So the first thing that they have to do is to make the problem dimensionless, adimensional. Okay? So in order for doing this, if you remember a couple of weeks ago, we were discussing some ways for doing this kind of procedure, saying that it would be useful in the future, and the future is now, for understanding, for dealing with differential equations or in general equations where you have terms which are subleading. So what was the idea? The idea is to find some characteristic scales and define dimensionless quantities with respect to these characteristic scales. Here in this equation, we have just one independent variable and the state variable that we want to determine, which are respectively the independent variable is tau, is the time, and the variable instead that we want to determine with in relation to tau is the velocity v. So what I have to find in order to adimensionalize the problem is a characteristic scale for the velocity and the characteristic scale for time. Question: what is a characteristic scale for this problem for the velocity?
B equal to 1.
Why?
Because if we have not B,
Who's B? Okay.
we don't have the correction of the velocity.
If you have V equal to 1, no. So actually the idea, remember, it's to find some kind of limiting scale for that specific variable. So what could be the limiting scale? I can tell you the answer. The answer is V naught. Tell me why the answer is V naught. The characteristic scale is this V naught here.
Because the velocity couldn't reach, for example, 1,000, you know.
Why? So because basically this model is telling you, oh, okay, you have this body which is moving somewhere in water, right? The starting velocity is v naught. So the body is starting with v naught. What do you expect that the body is doing? Slowing down. Right. It's slowing down. So the maximum velocity that this guy, this body can reach is the initial velocity, is v naught. Basically, it's slowing down because there is here this term which is telling me that is like breaking the body in the what's the name, in the medium. Actually, there is this other term which has the plus sign, but remember that this term here is by definition small with respect to the other one. So this guy is surely slowing down. This means that this capital V naught is some kind of limiting velocity. Fine, that's good. So this is a good characteristic length, good characteristic scale for velocity. Which means that I can already define some dimensionless variable y, which is given by the ratio between v, which is my state variable, the variable that I want to determine, and the characteristic scale, which is v naught. Okay, this is the first one. Now we need to find a second characteristic scale, which is the characteristic scale for time. Because in order to render the equation dimensionless, we need also to rescale the time, tau. So in principle, what I have to do is try to find some quantity that can be. Come on, it's not possible. Oh no. Well, I don't know if I was able or not to introduce the guy finally. Okay. So yeah. So we have to find some characteristic scale also for time. Remember that the characteristic scale should be something built out from the quantity that I already have. So from some mass, from these parameters A, B, and so forth and so on. So I have to find some combinations which is giving me some good characteristic time with respect to which I can rescale tau. All right, how can I find this? The idea is that I can look to the equation without the perturbing term. So what I'm doing is to look to the equation and derivative with respect to time of v equal to minus a times v. Okay? Why? Because okay, that's fine. These I know that v is much smaller than a, so I would expect that more or less the solution of this equation could give me an idea of what are the characteristic times playing in this process. Okay, and this equation is an equation that this is an homogeneous first order ordinary differential equations, which we have solved already a couple of times during these weeks. So what's the solution? Do you remember what's the solution of this equation? So this is a typical equation that you solve by separation of variables, right? So this is the typical equation that you solved by looking at the V over V equal to minus A over M in the tau, right? So what I'm doing is so what I've done, just put all the variables in tau on the right hand side and all the variables in V on the left hand side. And then what I have to do is to integrate. So here I will have some log V, and on the right hand side I will have some minus A over M times tau plus some constant critical case. Such a way that now if I'm exponentiating left hand side and right hand side, what I have is exponential of log V is equal to exponential of this thing here. But exponential of log V is V. I can factorize exponential of kappa, which is a number. I can call Pepe, I can call Josue, I will call it capital A, times the exponential of minus A over M times tau. So this this is the solution of again the differential equation without the correction. This solution is telling me one thing. What is a characteristic time? What is the characteristic time if I'm looking to this equation, to this solution? No, if I put tau equal to 0, what happens if I put tau equal to 0? Let's see. V equal to A, because tau equal to 0, I will have exponential of 0, which is 1, and then I will have V equal to A. You need a coffee, man. I will buy you a coffee, don't worry. So, the point here is that don't think about any limiting time. Time cannot have limits, right? So the idea is that you're looking for some time during which the process is showing some interesting behavior. Let's put it this way. Okay, what's this time? This time is basically set by the coefficients that you have here. Okay, now pay attention. The time is not A over M. A over M has the dimension of what? One over time. One over time. So basically, the characteristic, why? Because the quantity that you have here in this exponent must be adimensional, because I cannot take the exponential of elephants. I can take the exponential of some dimensionless quantity. So if I have exponential of elephants times some constant, this constant here must have the dimensions of 1 over elephant. Otherwise, this thing is not well defined. Okay? So in this case, I have A divided by M times tau. This thing here is dimensionless. Must be dimensionless, because otherwise I cannot take the exponential. So if this is dimensionless, A over M must have the dimensions of the inverse of time. Okay? But if A over M has the dimension of the inverse of time, what has the dimension of time? M over A. So M over A has the dimension of a time. And well, apart the fact that it has the dimension of time, the most interesting part is that m over a sets a good characteristic time for my process. Why? Because basically for tau, which is equal to m over a, the process tells me that the velocity has already decreased of a quantity which is 1 over e, which is typical in physics to say that is enough for having some kind of verifiable effect.
So my body is almost stopped.
More or less. Let's say that it's not completely stopped, but you can say that this is enough. So this scale is a good scale for seeing a change in the velocity of your body. Okay, the body is still not is not stopped, but this amount of time is enough. Is good enough for seeing that it has slowed down. Okay. Wow, because again, in physics, changes which are of the order of 1 over a, of 1 over e or e, are good enough, are supposed to be good enough for appreciate these changes. Okay, so the we have a time scale, a characteristic time scale, which is m over a. So we can define a dimensionless time, which is I will call it t, which is given from by the dimension full time tau divided by the characteristic time m over a. So this is the dimensionless time. We have defined before y to be v divided by v naught, which is some dimensionless velocity. Let me call it like that. So what I can do now is to take the original equation and find the corresponding dimensionless equation. What was the original equation? This one. So the original equation was m dv in the tau equal to minus av plus v squared. Okay. And now what I can do, what I would like to do is to adimensionalize the equation. So I have to I want to express the left-hand side in terms of dy in the t. So I want that the left-hand side becomes something like dy in the t. Okay, because this would be some dimensionless equation. So what I should do, how can I obtain the y in the t on this side? So here I have to multiply for something, right? For what? First of all, how can I obtain the y? That's good. So if I multiply times 1 over v0, this gives me from here the y is equal to the v divided by v0. So here I have the v divided by v0, which is the y. And now I need Now what I have to do is to do the same thing for the tau. Now from the tau, if I'm using this relation here, I know that the t is equal to the tau divided by m over a. So in order for writing the t, what I need, I can write also this as the tau a over m, right? But 1 over the t is equal to m over a 1 over the tau, correct? Okay, okay. So basically here I already have m, I have the tau. What I have to do is to divide by a. So in this way I have m divided by a 1 over the tau, which is 1 over the t. So again, what I've done is to start with my equation m, the v, and the t, and I multiply by 1 over v naught a. If I multiply, well, I divide it by v naught a. If I do this on the left hand side, I have to do this on the right hand side. So here is 1 over v naught a. Okay? Now let's see. The left hand side becomes the y and the t. Fantastic. What happens to the right hand side? The right hand side is minus a small v divided by a v naught plus b squared divided by a v naught. Now the first term here I can kill a, and here I have v divided by v naught, which is y minus y. Here what I have is b divided by a, then I have this is v squared, so it's v times v divided by v naught. But I have to construct something which looks like y. So what I have to do here, what I can do is to, well, this v over v naught is y. But then I need another v naught, so I have to multiply and divide by v naught again. Only this term. Such a way that I have another y here. So in total I will have minus y plus v naught divided by a times y squared. Now, don't forget that I have always this condition here, v which is much smaller than a. I can forget about b, a, v naught, blah, blah, blah. What I can do is to call this term here epsilon. This is, since b is much smaller than a, this is enough to ensure me that this epsilon is going to be much smaller than 1. So let me rewrite finally the dimensionless equation, so the adimensionalized equation. The y in the t is equal to minus y plus epsilon y squared. there is still the initial condition that we have to adimensionalize, right? So you remember we had an initial condition. The initial condition was B not equal, so B in tau equal to 0 is equal to B naught. What happens when I'm adimensionalizing this condition? How can I write the condition in a dimensionless way? Very good. Basically, this is you obtain this by dividing by the characteristic scale. So on the left hand side is y evaluated in tau equal to 0, in t equal to 0, and on the right hand side is just 1. So this is my dimensionless equation, the adimensionalized equation, with the initial conditions given by y naught equal to 1, and with the extra condition of assuming that the term in y squared, epsilon y squared, is small with respect to the other terms. Good, but now we have to solve the equation. So far we have just adimensionalized the equation. What we have to do now is to find an approximated solution to this equation. So in this case, and again, only rarely you can solve problems with the regular perturbation method. Let's solve that. No, I mean, for usual natural problem, natural phenomenon, you have to go to other perturbation methods. In any case, let's solve with the regular perturbation method. So for ODEs, the idea is that you are doing exactly the same that you do for the algebraic equation, for the algebraic case. That is, you are assuming that your solution y can be written as y naught plus epsilon y1 plus epsilon squared y2, etc. All these functions are functions of t. So y is a function of t, y naught is a function of t, y1 is a function of t, y2 is a function of t. So what I can do now is to take these ansatz and put the ansatz. No.
Is return.
Yeah. I don't understand. And put the ansatz in the differential equation. Okay, fantastic. Let's see what happens. So I have the derivative with respect to t of y, and y is y naught plus epsilon y1 plus epsilon squared y2 higher order terms. This is equal to minus y, which is y naught plus epsilon y1 plus epsilon squared y2 plus etc. And then I have plus epsilon times y squared, y naught plus epsilon y1 plus epsilon squared y2 plus other terms, everything squared. Sì, ci vuoi far morire soffocato, fa un caldo. All right. Great. So let's evaluate this equation explicitly. So we have the derivative of y naught with respect to t. Let me write it as y naught prime plus epsilon y1 prime plus epsilon squared y2 prime plus other terms. And on the right hand side I have minus y naught minus epsilon y1 minus epsilon squared y2 other terms. And then I have plus epsilon that multiplies what? Y naught squared plus epsilon squared y1 squared plus, well, the square root of epsilon squared is again epsilon to the 4. I don't need it. But I need the terms which comes from y naught times epsilon y1. This is twice epsilon y naught y1. Well, in principle, I need also the terms that comes from y naught and y2, which is 2 epsilon squared y naught y2. In any case, this will not contribute, and I will show you in a second. So what happens to these equations? This equation is the left hand side is the same. Let me write this in the same way. Here on the right hand side, the first part will be the same. The second part, I need just the terms up to the second order. So it's epsilon y naught squared and then this times this is third order. I don't need it. This times this other one is third order. I don't need it. The only one that I need is epsilon times 2 epsilon y naught y1, which gives me a 2 epsilon squared y naught y1. Hello? Hello? Okay. So what I have to do now is, you remember the same thing that we have done in the case of the algebraic equation. So in the case of the algebraic equation that we have solved at the beginning of the lecture, what we have done is to take the terms which are of the same order in epsilon and to construct equations from out of these terms. So let's do the same thing also here for the differential equations. Let's start with the terms which are of order epsilon to the power 0. So what are the terms in epsilon to the power 0? Is this one and this one. Right? So the first equation is y naught prime equal to minus y naught. Now let's take the terms which are of order epsilon. So we have this one, then we have this one, and what do I have? This one, right? So it's y1 prime equal to minus y1 plus y naught squared. Just. Now let's take the terms that are ordered epsilon squared. So it's this here, this here, and this other one here, which gives me y2 prime equal to what? To minus y2 plus 2 y naught y1. Higher the term is set up. So now what we have to do is to solve this tower of equations. Now the first equation is, again, it's a first order ODE, homogeneous one, which is solved by exponential equation. So yeah, there is something that I didn't tell you, which is basically I had to do the same thing also for the initial condition. So our initial condition was y evaluated in 0 equal to 1, right? So, but what I have to do is to write this y using my ansatz for the solution, which is this ansatz here. So basically this means that they have to do y naught in 0 plus epsilon y1 in 0 plus epsilon squared y2 in 0, higher the terms, equal to 1. So this basically gives me the initial conditions for this tower of equations. So the first initial condition is y naught 0 equal to 1. So I have to solve this equation here with y naught 0 equal to 1. The second condition is the one that I obtained from the order epsilon here, which does not have anything here. So basically means that the second condition is y1 0 equal to 0. The third condition is y2 0 again equal to 0. So in order to find a approximate solution, what I have to do is to solve these series of equations, and then these y naught, y1, y2 will be the terms in my approximated solution. Great. So what's the solution of the first equation? The first equation has a solution which is y naught of t equal to a times the exponential of minus t. This is the same equation that we have solved before. But I have the condition, the initial condition y0 in 0 equal to 1. So this means that y0 in 0 is equal to a times the exponential of minus 0. This must be equal to 1. This is the initial condition that I have, which basically tells me that A must be equal to 1. Right? So the solution of the first equation with this initial condition is y naught of t equal to the exponential of minus t. I can paste this. Pinguini, che sono queste cose? What's the second equation? The second equation is y1 prime equal to minus y1 plus y naught squared. But now I can use y naught squared because I know y naught squared. Okay? Y naught is e to the minus t. So y naught squared, this guy here, is e to the minus 2t. And I have to solve this equation with the initial condition y1 evaluated in 0 equal to 0. Now, in order to solve this, do you remember how to solve this equation? No, eh? I've done an appendix that you will find in the notes of this week with the way you can use to solve these equations. Let me tell you briefly how does this work. So the idea is that the general solution of an ordinary differential equation like this one can be written as the sum of the solution of the homogeneous equation plus the particular solution of the full equation. So the solution of this equation here, y1 can be written as a sum of solution of homogeneous equation plus particular solution of entire equation. Now, the homogeneous equation is basically the equation that you have if you don't have these terms here, this term here. Right? It's the equation without this. This is the homogeneous one. If you have this extra term, then the equation becomes non-homogeneous. That's the problem of this equation, actually. So what you have to do is to solve the equation y1 prime equal to minus y1, and this would give you the solution of the homogeneous equation. And then what you have to do is to solve, is to find a particular solution of the non-homogeneous equation. Let's do, I will not do entirely, again, it's in this appendix, I will tell you more or less what's the idea of the story. So the solution of the homogeneous equation, this is again the same equation of the one that we have solved before. So the solution is going to be some constant times the exponential of minus t. This is the solution of the homogeneous equation. Now the problem is to find a particular solution of the non-homogeneous equation. Now there are a number of methods that you can use, which are not complicated but are a bit long to do now. In particular, what you can do is to use a method which is called the method of variation of of constant, variational parameters, as you like. So the idea is that you look for a solution that particular solution of the non-homogeneous equation that looks like this one, where the constant k is not constant but depends on time. So you do an ansatz that you look for an equation like this one. Okay, so you do this ansatz and you try to relate the So you try to relate the I don't remember, I use S probably. You take this thing here, you put in the non-homogeneous equation, and you try to relate S to the non-homogeneous term. In principle, this should give you the particular solution for the non-homogeneous equation. Finally, the general solution is going to be the sum of this term here plus the particular one. Again, users, this is just calculations, blah, blah, blah. I mean, trivial calculations, just integrals, which are simple integrals, and you should be able to do this. So, what I want to tell you is that the solution of the final general solution of this guy here is going to be equal to e to the minus t minus e to the minus 2t. Okay, this is a solution which already takes into account the initial value also. So let me stop to the first order in epsilon. You can try to find the second order in epsilon. Basically, the idea is exactly the same. So the second order in epsilon is going to be some y2 prime equal to minus y2 plus 2 that multiplies y0, y1. But you know y0 and you know y1. So here, what you will have is a non-homogeneous term. Is some function of t. So this equation here looks like this one here, where this function here is different. So what you should do is to find that function using this method that I told you and that you can find on the appendix. Therefore, what is the approximated final solution for the problem, for the initial problem? The final solution is going to be some y, which is the sum of the different terms, different order in epsilon. So you have the y0, which was e to the minus t. Then you have epsilon times y1, which is e to the minus t minus e to the minus 2t, plus, well, higher order terms that we will find. Now, actually, you can do the same check that we have done for the algebraic equation, in the sense that we are cheating a bit because the ordinary differential equation that I showed you of this problem, so this equation here with this initial value can be solved exactly. So in principle, you don't need perturbation method to solve this equation. What you can do in any case is to look for the exact solution of this equation, write it in the perturbed form with respect to perturbing with respect to epsilon, and check if the perturbed solution that we found here is good or not. And you will find that it's good. Actually, this is the approximate solution is a good approximation of the exact solution of the ODE. Caspita! No, dai, ma sono solo ste bestie, no? No, un po' più no, dai ragazzi. Un po' troppo. No! Sta miseria. Minchia sta calma. Non è a caso. Non so per la finale. Lo so.
Si è posato
Non ci credo.
allora in una quadra.
Guardate che sei di credere.
Sta là, aspetta, partire di nuovo. Vai, accomodati fuori, forza.
Se non schiacci che fa.
Ma no, ma si può mai fare?
Un stagio da un calcolone.
Guarda che è pure quella finestra, Se non lo schiacci si adagia.
E tu rimane
Allora, sei più... Chiudi.
Sorry guys. All right, what's the yeah, right. In the next example, last thing for today, which is an example that possibly I will not complete, we will complete it tomorrow because I do not want to oblige you to stay here hours. In the next example, we are starting to write down an equation that will show you that this fantastic regular perturbation method doesn't work most of the time. So the idea, for example, is to study a system which is given by a mass and spring with the non-linear restoring term. So basically, when you have the system spring with the mass, the restoring term usually is going like minus k times the displacement, right? So let me write n times this y is now different from this one. The previous example is over. Now reset everything, so this y is different. Usually, when you have mass spring, this is the law of dynamics that that describe the system, right? Where k is the usual hook. This is the hook law. This is the hook constant, the elastic constant of the spring. Now, suppose that instead of being linear, the mass spring is has some non-linear term. So suppose that that the restoring term is modified by term like this one. You see here it's minus, plus, or well, would be, you can modify the law in different terms. Here there is a minus a times y to the cube. And this is evaluated with, this should be solved with some specific particular condition, initial conditions. What are the initial conditions? The initial conditions is y at time 0, which is going to be the amplitude, the maximum amplitude of the oscillations. Let me call it A. So imagine I have the spring, the body here, this thing which is oscillating. At the beginning, I'm putting the body at the maximum of the oscillation. Then I'm leaving it to oscillate. If I don't have this term, this would oscillate like this. If I have these other terms, this would change the oscillations in order to not have any oscillations anymore. So blah 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 blah, and the other initial condition, which is the velocity at time t. I'm starting with the spring which is still, it's like that. Okay, it doesn't move. This is equal to 0. Then I leave the system free to evolve, and it will start to move. But at the beginning, the velocity is equal to 0. Good. Now, what I have to do in order to start is to non-dimensionalize, adimensionalize the equation. So finding the dimensionless here. The dimensionless form of the equation, as we have done before for the ODE of the last example. So, how can we do this? Let's note let's consider first of all what are the dimensions of the different quantities which are involved in the problem. Okay, I have m, which is trivially a mass. Then I have capital A, which is this thing here. What's the dimension of capital A? The length. And now I have K. What's the dimension of K?
Newton over length.
I want the dimensions.
Yeah.
you can say by looking at the equation.
ky are the same dimensions of a, y, and q. So
And what's the dimension of a, y to q? Mass over? Mass over time. Why? On the other side. Almost there, because it's mass over time squared, because we have the tau squared. Almost there. So this is mass times t to the minus 2. Because this term here has the same dimension of this term here, but has also the same dimension of this. So it's mass times length divided by times square, but here I already have a length, so it's just mass divided by t minus 2. And then I have the dimension of A, and in the same way you can show that the dimension of A is mass L minus 2 t minus 2. Fantastic. Now, let me define a dimensionless y. My dimensionless y is gonna be, well, no, I'm using here y. U. So U is gonna be a dimensionless parameter, which is y divided by the characteristic length. The characteristic length is already there, is capital A. So this is good parameter. Right? What do I need? I need time. I need time in every sense. So what I do is to find some characteristic time as we have done before. How did we find before the characteristic time? We were solving the equations without the perturbing term, and then we were supposing that the time, the characteristic time appearing in the solution would be a good candidate for the characteristic time. Okay, great. What's in this case the equations that we would expect to be the one without the perturbing term? So the perturbing term is this guy here, correct? So the equations without this one would be m y double prime equal to minus ky, with the condition that y naught is equal to a and y prime is equal to 0. Y prime in 0 is equal to 0. Now, the solution of this equation here is a solution which is always in terms of sine and cosine, right? So if you're using also the initial conditions, what you can find is that the solution of this equation here with this kind of conditions is going to be something that goes like the cosine of square root of k over m times 1 over tau.
I'm sorry, Professor. Could you please explain again the dimension of car? I can't understand.
Yeah, all right.
Thank you.
There is a mistake here. I have to think about this because there is a mistake. About the dimension of k. So the dimension of k can be found by looking at directly at the equations that I wrote here. So the dimension of this term here, so k times y, must be the same dimension of a times y to the power 3, which must be of the same dimension of m times the second derivative of y with respect to tau squared. Okay? Now, I cannot say anything about this for the moment, but I can say something about this term here, because this term here has a dimension of m, which is a mass, times a y, which is a length, times divided by a time squared, which is then t to the minus 2. So here I have the term k times y, but y has the dimension of a length. So in order for this term to have the same dimensions of this other term, what I have to do is to suppose that k has the dimension of m times t to the minus 2. In this way, this and this are the same. So k has dimension m times t times minus 2, which is what is written here.
Yes, Professor. Thank you.
That's okay. So back to the problem. What I need here is tau. Okay, sorry, this tau is not here, this tau is here. Right. Sorry. So basically, what is this telling you? This is telling you that you can define some characteristic time which is given, as in the case of the exponential, right? So which is given when this expression, again, this expression must be dimensionless. So this means that the square root of k over m must be equal to, must have the dimension of 1 over time. So a good time scale, good characteristic time, can be set by the square root of m over k. Actually, you can check because the dimension of m is mass. The dimension of k is mass times t minus 2. So this square root of m over k has the dimension of a time. This is a good time scale. So finally, we can define a dimensionless time t, which is given by tau divided by the square root of m over k. So I have a dimensionless length, let me call it like this, which is this u, and the dimensionless time, which is this t. Such a way that finally I can write my equation in a dimensionless way. So the equation was m the squared y in the tau squared equal to minus ky minus ay at cube. So now we have to do exactly the same thing that we have done before for adimensionalize. What I can do is to, let me tell you directly, I'm dividing by a times k, both sides of the equation. If I divide by a times k, here I have y divided by a is u. And from here I have that tau is equal to, sorry, that t is equal to d tau divided by square root of m over k, which basically means that t squared is equal to d tau squared divided by m divided by k. Which is the combination that I have here. So this is the second derivative of u with respect to my new parameter t. What do I have on the right-hand side? On the right-hand side, I have k and k. You can simplify k and k, so you have y divided by a, which is u. And then I can do the same trick that I did before. So multiply and divide by a squared only the second term, in such a way that I have this term here, which is u cubed. And then I have small a, capital A squared divided by k. Oh, no, dai. Me era penduto oggi. Let me call this thing here epsilon. I'm supposing that A is much smaller than K, because I'm supposing that this is just a perturbation on top of the total dynamics of the system, the behavior of the system. So this is minus U minus epsilon U to the cube. This is what is called the Duffing equation. This equation here. Now, if you try the regular perturbation method, so if you try to solve this equation looking for a solution u written as u0 plus epsilon u1 plus epsilon squared u2 plus blah blah blah, you run into some problems. Why? Because basically, well, I'm not going to do this calculation because this calculation is not useful at the moment. U0, I can give you the solution. U0 is going to be something like cosine of t, which is okay. U1 is going to be something which is like 1 over, well, some expression. So the big problem for this equation is given by this term here. Because when you put u0 and u1 and u2, etc., into your ansatz, okay, you will end up with, for this term here, you will end up with something which goes like epsilon times t times sine. Sine is not a problem. The problem is epsilon times t, because if I choose an epsilon which is small, at a certain point, at a certain time, the term epsilon times t will be large, which is something that does not happen with the other terms. Here you have cosine of t, cosine of 3t, cosine of t. These terms are bounded between minus 1 and 1. This term here, epsilon times t sine t, have this part epsilon times t, which cannot be controlled for t that goes to infinity. So this, what does it mean? This means that this approximation works only for some limited amount of time. So once that you define, once you say epsilon is this, epsilon is 0.0001, the approximation works if epsilon times t is small. When epsilon times t becomes, when t becomes 1 billion of billions, epsilon times t is not small, and the approximation is not good anymore. So the regular perturbation method loses the validity. So these kind of terms are called secular terms. And we will stop here. And tomorrow we are starting by looking for a method for solving the Duffing equation bypassing the secular term. Somebody that has a question there? Okay, everything is fine. Thanks a lot to everybody and talk to you tomorrow. Cheers, guys.
Thank you, Professor. Bye-bye.
Bye.
Thank you, Professor. Bye-bye.
Cheers. Ciao.
Thank you, sir.